In this video, we're going to discuss seafloor spreading, a key geological idea and one of the foundational concepts behind plate tectonics. To begin, we're going to go way back to the early 1900s and a German meteorologist named Alfred Wegener, who was proposing a radical new idea that he called continental drift. This idea proposed that the continents were not stationary masses, but rather slowly moving slabs of rock that interacted with one another over time. But in order to really make sense of this idea, we need evidence. Now, fortunately, after Wegener's death, evidence became available in a variety of forms, and that evidence also describes the process that we now know as seafloor spreading. So in this video, we're going to look at these four key pieces of evidence to support and describe this idea. The first thing we're going to look at is the ocean floor. Now, in the days of Wegener, we were limited in the amount of data and information we had about the sea floor. For hundreds of years, we had been able to collect some crude information by doing methods such as line sounding, where you would drop a rope with a weight on the end down to measure how deep different parts of the ocean were. And if you did this in enough areas, you can create a simple and basic map of the ocean floor. Unfortunately, these maps were, as I mentioned, very crude and very limited and unreliable. But as World War I began and ended, and then eventually World War II came about, the United States launched a Department of the Navy Office of Naval Research, and for the first time, science was driving an effort to map the ocean floor. In fact, scientists Marie Tharp and Bruce Heezen developed the first bathymetric map of the Atlantic Ocean, and this is in the 1950s. They used a technology known as sonar to map accurately the depth of the sea over large areas. And they created a map that was the most accurate of its time. And so if we were to look at the world today and actually take the blue oceans and drain them from the surface, what we would see is that the sea floor is not a vast expanse of flat desert, as was believed beforehand, but rather it was a jagged and active area with giant peaks and cracks, trenches, earthquakes, and active volcanoes, as you can see here now that we've drained out the water from the earth. If we zoom in on different areas, particularly the center of the North Atlantic Ocean and extending down through the southern Atlantic, you see this massive scar, this thousands of mile-long mountain range that runs down the Atlantic Ocean basin and essentially mimics the shape of the continents. This set off some alarm bells for scientists, as they believed that this could potentially be related to Wegener's earlier theory of the moving continents. After the work of Tharp and Heezen came along other notable scientists, including Robert Dietz and Harry Hess, who published work that further described the fascinating geological structures that are found in the bottom of the ocean. In fact, if you were to draw a profile from North America to Europe, you would see something like this, with vast expanses of flat areas and then that jagged, irregular central mountain range that runs down the center of the Atlantic Ocean. And so this simple observation that the seafloor has geology became supporting evidence number one. So there are active fractures in the lithosphere, or the crust of the ocean floor, in a pattern that appears to mimic the shape of the continental coastlines. Based on these observations, scientists like Hess developed an idea that along this ridge, magma from underground magma chambers was spewing up through the crack in the Earth's surface and pushing the plates apart, pushing the slabs of rock on either side away from one another, in what would become known as a spreading center or a divergent plate boundary, as seen in this animation here. Slowly over time, the plates spread apart, carrying the rock and the sediment with them. And along this boundary, we see lots of cracks called faults and scarps in the surface of the Earth. Here's another diagram that illustrates what we think happens along these spreading centers, where magma pushes its way up through the crack and spreads the plates apart above. And so one of the ideas was to look at how old the rock on the seafloor is, as that could potentially support this notion. And if you were to map the age of the seafloor, similar to what we see here, what you would notice is that, shown in red, we have very young rock right along the ridge. And then as you go away from the ridge in either direction through the orange and yellow to the green and then blue, the age of the seafloor gets older. And so the only way that's really possible is if in fact seafloor spreading is occurring, and that Harry Hess and other scientists were correct in their theories. So supporting evidence number 2 is that the age of the seafloor rock increases as you get further away from the mid-ocean ridge. But as with all science, we're constantly looking for more supporting evidence. And so scientists went back to the drawing board, and they thought about other things that could prove that this is in fact happening. So something else they decided to look at was sediment. Now, sediment refers to sand and clay and other bits of rock and organic matter that settles on the bottom of the ocean. Similar to the idea that young rock should be found near the mid-ocean ridge and old rock should be found further away, scientists believe that sediments should become thicker in their layers as you get further from the ridges, which makes sense because older rock would have had more time to accumulate sediment, as you can see in this diagram. If you were to travel along the seafloor from point A to B to C to D, you would notice that that layer of sediment increases in its thickness. And that's because the rock is older and there's been more time for the accumulation of that sediment. And this proved to be true as we studied the seafloor more and more, as with this map showing sediment thickness with different colors, with the dark blue being thin layers of sediment, and light blue to green to yellow and red becoming thicker and thicker. And so that gives us supporting evidence number 3. The thickness of the layer of sediments deposited on the ocean floor increases as you get further away from a mid-ocean ridge. And so once again, we would look to warfare and the Navy to get more scientific information to support the concept. Now, during World War II, one of the issues that the Americans and our allies were dealing with was being able to identify these massive sea mines and submarines that were being used by the Germans. And so one thing we did was begin to study magnetism. Using new technology, we could travel across the ocean in a boat or in an airplane and detect the magnetic field under the ocean's surface. Now, submarines and mines give off a certain amount of magnetism or are sensed by this equipment, and so we are able to actually detect them even if they're out of visible sight. But we also were able to detect magnetism of the sea floor, and we found something fascinating, which is that if you look at the magnetism of the sea floor in different areas, it's not random as you might expect, but rather you see these bands or stripes of alternating magnetism, as seen in this diagram or this one here. Now, in order to really understand this, we need to step back a little bit and actually look at the inside of the Earth. In case you were unaware, the inside of the Earth is made up of different layers, and one of those layers, the outer core, shown here in orange, is composed of molten metals, including iron and nickel. Now, those molten liquid metals are not sitting still, but rather they are flowing around the inner core, and the movement of that liquid metal generates a magnetic field, which essentially turns the Earth into one gigantic magnet. Now, the fact that the Earth is a magnet and has a magnetic field is very important for a lot of different reasons, which we won't get into in this video, but it's important that you know the Earth essentially is a magnet. And just like a magnet that you would play with, it has both a north and a south pole that behave a little bit differently and are detectable. Now, a strange phenomenon we have seen on Earth is that the magnetic north and south poles switch periodically over time. So if you look at this visualization, let's say that the orange area represents the magnetic north and the blue represents the magnetic south. Now, over time, those poles will become kind of all haywire and then eventually flip, so that north has become south and south has become north. This is known as a magnetic reversal, and we see it happen on a fairly regular timescale throughout Earth's geologic history. Now, here's why this is so important and relevant to seafloor spreading. It's because these magnetic reversals are captured in the solidified rock on either side of a mid-ocean ridge. As magma wells up through the ridge and hits that cold ocean water and solidifies into rock, minerals within the magma align with the Earth's magnetic field. And then we forever have a record of what the Earth's magnetic field was at the moment that that rock formed. Let's look at this animation, which shows it clearly, that as magma upwells and solidifies, it records the Earth's magnetic field. And whenever those switches occur, we see it as a record within the rock. Now, it's shown here with different colors, black and white, within the rock, which of course is not the case in reality. However, if we could see the seafloor magnetism, we would see patterns that look kind of like this. If we were to come back over this area with a boat and measure it, what we would see is that the pattern of magnetism matches up perfectly on either side of the ridge. Where we see positive magnetism on the left side, it aligns with a similar band on the opposite side. And the only possible way that this pattern could exist is if the seafloor is spreading. And so this becomes supporting evidence number 4. Patterns of seafloor magnetism on either side of a mid-ocean ridge matches up with one another. And so this gives us a complete case that proves that the seafloor on Earth is in fact spreading apart and that plate tectonics is a real phenomenon. So when we look at the Earth and we see these fascinating structures under the ocean, we now understand why. All we have to do is look at these 4 key pieces of evidence. Just to review them quickly, here they are. Number 1. There are active fractures in the lithosphere along the ocean floor in a pattern that mimics the shapes of the continental coastlines. Number 2, the age of the rock of the seafloor increases as you get further away from the mid-ocean ridge. Number 3, the thickness of the layer of sediments deposited on the ocean floor increases as you get further away from the mid-ocean ridge. And finally, number 4, patterns of seafloor magnetism on either side of the ridge match up with one another. And so now we accept the fact that the oceans are in fact spreading apart and that continental drift and plate tectonics are true phenomenon that we see on Earth. Thanks for watching.